Welcome back to another video. Our previous video looked at how we could augment sample selection correction methods like those pioneered by Jim Heckman with machine learning classification algorithms. And in this video, we're going to explore a very popular method called double debiased machine learning. And this is highly useful in a number of applied econometrics settings where we want to purge the confounding factors of a high-dimensional set of regressors so that we can estimate a treatment effect parameter. And this paper that we'll talk about is highly influential and has nearly 5,000 citations on Google Scholar, despite being published for less than 8 years at the time of recording. And to set up the problem, we want to think about LASSO and how it could improve causal inference. So the idea is we have these off-the-shelf model selection procedures from machine learning that maybe we could apply to causal inference questions. And so if you think about it, maybe we have a matching problem or a regression problem, and we are relying on the unconfoundedness assumption. But if we have high-dimensional data, we feel like we can control for everything. And yet we have so many covariates that maybe we actually can't control for everything because that would violate the OLS rank and order conditions. But if we could control for everything, we'd have a really high R squared. And so maybe this would resolve any omitted variable bias that we have. And then LASSO can potentially give us the most important confounders and get rid of the other ones. But then the question is this going to have any econometric consequences if we do this? So the problem with the example I just gave is that LASSO is a prediction algorithm, but we need something for causal inference. And we know that those are not the same objective. And in particular with LASSO, if we take a slightly different sample, it will select a slightly different set of variables. And this again is because LASSO is just trying to predict, it doesn't care about causal inference. And so as Mullainathan and Spiess illustrate in their seminal Journal of Economic Perspectives paper, you can have two very different functions that produce the exact same prediction if you have LASSO in a high-dimensional setting. And so this is just an example of why we need to be more principled about bringing in these machine learning tools into econometrics. Because if we're not careful, they can actually undermine the econometric objective that we're trying to fulfill. And if we think about classical econometrics, we want estimators that are consistent and asymptotically normal. And so the setting in this double debiased machine learning paper is that we have a treatment effect that we want to estimate in a semi-parametric setting, and we have a high-dimensional model. And we're assuming that U is conditionally independent of X and D. And so we might be tempted to use LASSO or Ridge or any of the other machine learning algorithms that I talked about a few videos ago, since X is high dimensional. And this will solve the bias variance trade-off in terms of the machine learning aspect, but it will actually introduce regularization bias into our econometric estimate of interest, which is theta hat. And so this paper has a lot of very famous econometricians on it working together to solve this important problem. So it's not a surprise that it's been cited so widely and implemented so broadly. And what the paper comes up with is we can solve this problem of the machine learning injecting regularization bias into our estimates by adding another equation. So we want to think about the outcome and the selection equations separately. And we can think about what's happening here. So the selection equation is just going to be a function of x and some error term v. The outcome equation is going to be a function of treatment and x and some error term u. And we assume conditional independence for both error terms. And basically what we need to do is to orthogonalize D using this second equation. And then once we've orthogonalized D, we can estimate the parameter theta. And so we're going to use any machine learning algorithm we want to estimate the mapping M of x and G of x. This is where it gets the name double machine learning. And then instead of putting D in our outcome equation, we're going to use the orthogonalized nu, or nu hat. Maybe it's a v hat. So we're going to take the residual of the selection equation and plug that in our estimation of our treatment effect. And if you've ever learned about control functions in a prior econometrics class, this is somewhat related to that. So what are the steps that we do to produce this estimate? Well, first, we need to divide the sample into half or into k separate folds. And we're going to estimate the selection equation parameters in a first fold. And then in that same fold, we're going to estimate the outcome equation residuals. And then in the opposite fold, we're going to combine the information from both of those to get our estimate theta check. So if we just did theta hat using something like the Frischwall-Lavelle theorem, that would give us a biased theta hat because of the regularization bias involved. And so we've done this halfway in one fold and halfway in another fold. And then we repeat these steps and do them in the opposing folds that we did before. This is called cross-fitting. And then we get our final estimate, which is just an average across the two sets of results. So they show that this estimate theta check is going to be approximately unbiased and asymptotically efficient. And so that's how you do this famous double debiased machine learning algorithm. And if you go online, there's a whole Stata page for how to do this in Stata. And you can do all sorts of different machine learning algorithms to get those G hat and M hat estimates. And if I have time a little bit later, I'll post a video about going through and replicating some results from a prior analysis using those tools. So that's it for this overview of double debiased machine learning. In the next video, we'll talk about a related method called post-double selection that has a lot of similarities to this double debiased machine learning approach. And that post-double selection method can be really useful in a lot of applied regression settings that you might be encountering. So stay tuned for that, and thanks for joining this one.